up into, you can imagine it as three parts. First, I'll be going over half of the Ingrained tool focused on material surfaces. Then Chaitanya will go on to explain how the tool can be used for analyzing grain boundaries between materials. And he will finish the talk by describing an evolutionary algorithm that has been developed to merge the exploration of energy landscapes with the matching of experimental results, so that there's a automatic synergy between or automatic feedback loop between the two. So my name is Joshua Paul. I'm a postdoc under Maria Chan at the Center for Nanoscale Materials. My work primarily focuses on analyzing material surfaces and low-dimensional systems. Chaitanya, if you'd like to introduce yourself.
Yeah, thanks, Joshua, and thanks, Alvaro. So my name is Chaitanya Kolluru. I am also a postdoc with Dr. Maria Chan at the CNM Argonne. So my work primarily focuses on method development for structure inversion problems, from characterization data to atomistic structure, and also theoretical characterization once we have the structure, and use theory to get to know these materials better. Thanks.
Alrighty. I'm preaching to the choir a little bit here, but the question of how theory can be used to help, sorry, the windows are in a bit of a way. How theory can help the materials community. So this has been an ongoing effort ever since the Materials Genome Initiative was introduced and things really started to get rolling back in the early 2010s. But simply put, by using theory, experimental efforts are able to be accelerated, guided by the theoretical discoveries. So instead of trying to search through tens of thousands of materials for something that'll work for their problem, instead, they only have to search through 10 or so. That's much more reasonable for a PhD student or a postdoc to manage. Further, once the experimental results have been produced, that can inform the theory on the system that is being investigated, thus, or such that we can investigate the actual underlying physics for the phenomenon being observed, which can then pursue or feed into the pursuit of other similar materials that might perform even better, or introducing defects, or further controlling the synthesis of specific phases, that sort of thing. And so in Dr. Maria Chan's group, this is what we pursue. For two examples, on the left, we have the a high resolution STEM image, so scanning tunneling electron microscopy, that is used to image the grain boundaries between two materials. On the right, we have a STM image scanning tunneling microscopy for discovering a novel 2D material, borophane, that I'll be going over later. So the questions of being, what is the actual atomistic structure of these experimental images? Sure, the images provide a good amount of information, but we don't actually know the underlying atomistic structure. We can make guesses based on the images, but there was previously no explicit way to really identify the surface. In the case of STM images, what's being measured isn't atomic positions, it's the partial density of states of the system. And so what appear to be raised features can actually be physically lower in the system, and what can appear to be lowered parts of the image can actually be raised features physically. So there is nuance to analyzing these images that we can hopefully address. So, as I outlined previously, we're going to start with the Ingrained tool for surface structures using the STM mode. Then Chaitanya will go on to describe the TEM mode. And finally, he will explain how the multi-objective evolutionary algorithm we have called FANTASTX can be used to automate the process of characterizing the structures of these materials rather than pursuing examples by hand. So for the STM images, we have the experimentally observed structure, the STM image, and we have the desire to discover the phase for that underlying structure. So we use we use various tools in order to actually make that comparison, and as a result, characterize the underlying structure of the STM image. So on the left here, I have plotted the STM image for the pristine Cu2O cuprous oxide 111 crystalline facet. On the center here, we have what the candidate structure is for that pristine surface. And on the right is an overlap of the theoretical simulated STM image that we generate for that center structure. And below that, the experimental STM image. And you see that we end up having a fairly good fit. You see the periodicity across this direction matches well. You see the bright yellow spots surrounded by red, all blended together. The periodicity in both directions match well. And the amount of difference between the pixels of the experimental and theoretical images is low, indicating that we have a good simulation of the STM surface. The way this is done is by using the Tursoff and Hammond approximation and density functional theory, a software that is a theoretical framework that is used in order to solve Schrodinger's equation, or approximate the solution to Schrodinger's equation, and as a result, characterize the crystal and materials bond length, electronic properties, atomic positions, crystal structure, those sorts of things. The way that we end up using this DFT software in order to match the STM image is by calculating the partial charge density from DFT. Like I mentioned, STM measurements don't calculate exact atomic positions. It calculates the partial density of states of the electrons at a given bias voltage. So for our system, we have our theoretical crystal structure, and we have the surface. We have an imaginary STM tip, and then we have various parameters that are tuned. We have the partial charge density from DFT, but we don't just have a single isolated bias voltage. We have a window because DFT is an approximation. And so as a result, you're going to want to have a little bit of a window of partial charge densities to scan through when you're trying to match against the experimental image. You have a simulation of how high above the surface the STM image is being captured, how deep into the surface that this imaginary tip is capturing the partial density of states, and various other tuning parameters, such as the amount of smearing of the experimental image of the theoretical image, because experimental measurements aren't exactly precise. There's going to be some amount of blur due to the resolution of the machines. And so we simulate that with a blur that we apply on our perfect image. We can also stretch and squash the image, rotate the theoretical image relative to the experimental, all sorts of optimization parameters that are automatically passed through. On the right, we have for the theoretical image, or a theoretical system we're making a guess for, what the initial image is based on the parameters that we input. Well, this is all fine and dandy, but this is just based on one set of input parameters. What we want is to optimize those parameters to try and get a better approximation to the experimental image. And so, there we go. What happens is the parameters are perturbed, altered, optimized. A match is made against the experimental image, and a new score is generated identifying the amount of mismatch between the experimental image and our theoretical STM simulation. And you see here the Ingrained software passing through at the beginning, not so great a guess, but it starts to move around, converge, and eventually get a pretty good fit. Then we end up having a final infused Ingrained-STM simulation overlaying the theoretical and the experimental, so you can see just how good those results end up being. This was applied to the borafane system, which is hydrogenated borafene, a 2D material. The experimental collaborators for this project were measuring the surface using STM calculations, but they weren't sure exactly what the underlying structure was, namely where the hydrogen was actually located on this surface, because there were a few possible positions. Well, the Ingrained-STM tool was able to generate STM images for 3 positions of the hydrogen on the surface and match these theoretical structures to the experimental image. And so what you end up seeing is that the 2H position forming a rectangular pattern ends up being a fairly good match for the bias voltage at 24 millielectron volts, and a fairly good match against the 100 millielectron volt bias for the experimental images. That is one thing to note for the software that I'll get more into later, but the STM images are taken at a specific bias voltage relative to the Fermi level. We replicate that with DFT, but that is one point that you're pinning against. If you have the option with an experimental collaborator, ideally they're able to take multiple bias voltage images, and that provides more avenues to validate theoretical results against experimental. Now, the thing about Ingrained is that it's solving a local optimization problem. Like I said, you give a start of input parameters. Those are optimized against the experimental image, and you reach a ground state of accuracy over time. However, if you alter those starting configuration or those starting input parameters, then you can possibly converge on a different local minimum. On the bottom here is Ingrained run with 4 different sets of starting parameters for an experimental system. You see here that they converge on similar structures, but there are nuances. Here you get a wiggle pattern that is mostly consistent throughout. Here you get bands that get thinner and thicker. Here you get more atomically resolved wiggles. And here you get flat, consistent bands. Now, which of these is right or wrong depends on the experimental image, and that is matched against and a score generated. But this goes to show what the Ingrained software is able to converge upon in the importance of starting from multiple points to explore the possible experimental or theoretical space. What it also does is show how good the Ingrained software is at generating theoretical images. It is not necessarily limited to a specific kind of resolution experimental image or a specific kind of pattern. It is able to converge on, in this case, various solutions that match better or worse against the experimental image. So it's a fairly versatile tool. However, with that all said, you'll want to run what I call the multi-start approach. On the x-axis here, I have various candidate surfaces. On the y-axis, I have the scores for Ingrained fits. And with the box and whiskers, I have plotted for each of these candidate surfaces what the possible or what the best fit scores were. In this case, a lower score indicates higher similarity between the theoretical and experimental images. You see here that in some cases, the solutions end up being a fairly broad range depending on what your starting points were, whereas in other cases, we end up having a fairly narrow, concise range. This latter case ends up indicating that you have a good candidate surface. Basically, what that indicates is regardless of the variation of your starting point, Ingrained converge upon similar solutions rather than finding an outlier or a few outliers that indicate a good match. You are consistently able to get a good match, and that candidate surface is more likely to be viable. A few additional notes for the software. We have tools to automatically identify the angle between your STM image, your theoretical and experimental STM images. However, we recommend communicating with your experimental collaborators to figure out what the underlying direction or orientation of the substrate is and matching your simulation using that same angle. Images should be saved as monochrome, not multi-channel. The final mismatch score that you get is going to vary depending on your experimental image. Like I said, the amount of mismatch or the score that's generated, the lower the score, the more similarity between your images. And so depending on the resolution of your experimental image, you're going to have a floor on how accurate your theoretical image can be. So you'll want to fit the actual window for your theoretical image against your experimental image. You saw previously that the theoretical image wasn't the entire range of the experimental image because you want to be able to scan across to find the best match. But if your window's too small, then you're not going to necessarily capture the right periodicity. And finally, I highly recommend when working with your experimental collaborators to have them take multiple voltages or bias voltages for their experimental image so that when you have a candidate surface, you can perform an ingrained optimization at both those biases so that if a good solution is converged to at both those voltages or all three of those voltages or however many you do, that indicates greater likelihood that your theoretical surface that you're proposing matches the underlying experimental surface that was characterized. So now I'm going to hand things over to Chaitanya in order to present on the TEM version of the software and the FANTASTX algorithm.
Okay, thanks, Joshua. Joshua has explained about the first part, which is the STM mode of the Ingrained software. So now I will walk you through the TEM mode of the Ingrained software and also show an example where we use the Ingrained TEM mode to characterize the grain boundary of a material and find its structure and unravel interesting phenomena. So the Ingrained TEM mode, so we start with an experimental TEM image. Just a second. Okay, so we start with an experimental TEM image of a grain boundary specifically, and Ingrained TEM mode needs the information of both the individual grains, such as what's the chemical composition and what is the space group, and the projection perpendicular to the screen and also in the upward direction. So once we provide these information to the Ingrained software, it pulls the relevant structures from the materials project database corresponding to both the grains, and then it will fuse them to create a bicrystal structure. And then it creates a simulated TEM image from this bicrystal structure, and that simulated TEM image is optimized so that it matches well with the underlying experimental TEM image, similar to what we did in the STM. So here we are going to apply the Ingrained TEM mode on NMC cathode material. So NMC 622 is a layered cathode material, which is predominantly used in the lithium ion batteries. So they have these so-called low angle tilt grain boundaries, which are still present even though they claim in some of these single crystal cathode materials. And in this particular work, our experimentalists have hypothesized that having these low angle tilt boundaries, even though they are very stable and defect free, might still cause some oxygen loss, which is detrimental to the performance of the battery. So we have taken a small section in this low angle tilt boundary. As you can see, there are two grains. The top grain is aligned in this direction and the bottom grain in the opposite direction here. And there is a region in the middle which corresponds to the interface. So we have taken this grain boundary image as our target, and we also gathered the corresponding input parameters for both the top grain and the bottom grain, and we fed it into the Ingrained model, which pulled this particular bulk structure from the materials project database and created a bicrystal postcard. So here we show a reduced size bicrystal, because we wanted to perform DFT calculations. So we try to constrain the size to as minimum as we can while minimizing the strains within the cell. And here we have the simulated TEM image corresponding to the bicrystal. And when we overlay it on top of the experimental TEM image, we can see the rhombus-like pattern that has been observed in the interface of the experiments. So this gives us makes us fairly confident about the grain boundary structure. So now we go ahead and use this structure to perform DFT calculations and calculate the oxygen vacancy formation energies in the grain boundaries. And in like fully lithiated structure, and we remove the lithium to mimic the charged condition of the battery, and also calculate the oxygen vacancy formation energy. And interestingly, we find that the oxygen is more stable in the bulk, and the oxygen vacancy formation energy is much lower in delithiated grain boundary structures. So this kind of supports our hypothesis that having these low angle tilt boundaries, even though they are energetically stable, it will still cause oxygen loss. And also these 1D channels, they may help in reducing the diffusion barriers and further exacerbating the oxygen loss in these cathode materials. So overall, we showed about the two different modes of the ingrained package, the TEM mode and the STM mode, and we showed how we can go from experimental data to the atomistic structure. And later we also showed how we use the structure to understand the underlying phenomenon in these materials. So now the next challenge we have is, in majority or in most cases in the grain boundary STEM images, we find that the interface structure is not exactly similar to either of the grains. So here we have this zigzag snake-like pattern in the interface, which we know is tellurene. However, if we only consider creating an interfacial structure with the knowledge of the grains, we'll get something like this, which is not sufficient to describe the phase in the interface. So we have to do local optimization near the interfacial region, either using density functional theory or molecular dynamics. So this leads us into our next software package, FANTASTX. So where we perform this multi-objective optimization in order to get these interfacial metastable structures or unknown phases in experimentally observed materials. So FANTASTX stands for fully automated nanoscale to atomistic structure from theory and experiments. So we use both theory to calculate the thermodynamic energy corresponding to its stability. And also we take the relaxed structures and calculate the experimental simulation data, like the experimental TEM image, simulated TEM image, simulated XRD pattern or STM image, and so on. And we compare the mismatch between the simulated data and the actual experimental data. So we perform this multi-objective minimization in an iterative manner, and that will give us a final set of solution structures that's corresponding to these unknown phases. So what we have is the characterization data from the experiments. And what we want is the exact atomistic structure corresponding to the unknown phases or unknown regions found in the experimental data. So, so right now, our goal is to implement all these different experimental characterization methods in the software. Right now, we already have implemented the STM mode, TEM, XRD, PDF, and XIS. And this is the FANTASTX team that developed the software. So this is the overview of the FANTASTX. So FANTASTX is an evolutionary algorithm. So basically, we first sample a few candidate structures from the entire potential energy landscape that are representative of the full search space. And then for the initial population, we relax their structure and calculate their fingerprint and make sure these created structures are unique, which means they are not already evaluated. And then we perform the simulation on the relaxed structure, and then we take the mismatch, which is one objective function, and the energy, which is the second objective function, and we create an overall value using another objective function. And then we use this overall value to select parents in order to create a child structure and continue this search process. So we developed the FANTASTX software in a modular fashion because we wanted to incorporate different kinds of experimental simulation inversion capabilities. And also it can be easily extended to different geometries. In its current state, it currently supports bulk, nanoclusters, surfaces, grain boundaries, and molecules. These are the different structural geometries where we can perform the search. And also we can perform different simulations, like inversion of different simulations, like PDF data, TEM data, ZANES or XAS data, XRT spectrum, or STM images for surfaces. And we can either perform multi-objective search by trying to minimize both energy and simulation mismatch, or we can perform individual structure search, for materials discovery in a chemical space. So to give a brief overview of the genetic operators, so genetic algorithms work similar to the biological evolution, where the features in a structure that correspond to low energy or that contribute towards low energy will be propagated in subsequent generations. And we aid that process using mutation or mating, which corresponds to exploitation or exploration within the potential energy landscape or the search space. So here we have a parent structure, and we altered the atoms, the distances between the bonds, so that we can jump from one basin to a basin which is in the vicinity of this initial basin. So this is the exploitation parameter, or the operation. And in the mating operation, we take two different parents or three different parents and collect the features between these parents and combine them together to create a child structure. And this corresponds to the exploitation, where we have two different parents corresponding to two regions in the landscape, and we are going to a third space with combining these two parents. And since this is a multi-object evolutionary algorithm, we have two different objective functions. On one axis, we have the energy, which is which corresponds to the thermodynamic stability, and the another axis corresponds to the experimental mismatch. So which results in this kind of distribution, and we are looking for structures that are close to this axis or origin. So we will get a Pareto front of structures, where some structures will have very high energy, but they match well with the experiments. And some structures will have very low in energy, but they are like, they have very high mismatch with the experiments. So we take all these structures as potential solutions, and we can use these structures to further evaluate the phases. So here we use two different algorithms. So one on the left is called distance from Pareto, where we create a convex hull with the Pareto points, and we calculate the distance, perpendicular distance of each point from the convex hull. And that corresponds to the overall value of the data point. And that is used to determine the selection probability for that particular point. On the right, we have the epsilon MOA multi-object evolutionary algorithm, where we have epsilon values for each objective function, and this determines the grid size. And within each grid, we will only choose the one that is closest to the left corner here. So in this particular example, we have three different points in the same grids, but we will end up choosing this point as the representative of this particular epsilon grid. So the finer we choose, the more the data points will be included in the population, and the sparse the grid, the lesser we'll eliminate repetitive structures. So we use both of these methods and try to find the interfacial structure in the cadmium telluride tellurene grain boundary. So first we define the grain boundary structure, and we already have a fairly good match corresponding to the bulk of the top grain and the bottom grain, and we only vary the interface region. So after performing the FANTASTX search, using both the objective functions here, we plot here the objective function values of all the data points on objective function 2 and objective function 1. And we can see there is clearly one data point which is minimum in both axes. So we don't have a Pareto in this particular example, because our solution, which matches the experimental TEM image, is also thermodynamically stable structure. And we were able to find the same structure using both the searches with FANTASTX. And in another example, here we have a blue layer iridium oxide, which is polymorphic. So it shows a very high catalytic activity. And this is the experimental PDF data for the blue layer iridium oxide. And in this particular work, the best guess structure they have here is a cluster taken from the rutile iridium oxide. And you can see the fit, it gives a good fit, but does not give like a exact fit corresponding to the experimental PDF. And another issue is what we have in the experiments is a amorphous bulk phase, whereas the atomistic structure we have here, which is our best guess, is a nanocluster. So this again gives like a good problem where we can use FANTASTX to find the bulk structures that correspond to this experimental signal. So we perform this grand canonical search where we vary the composition of oxygen and iridium within a range and search for various bulk structures that match the PDF data. Again, we perform the search using both distance from Pareto and epsilon MOE algorithms. We use WASP again here. And as you can see, in this case, there is no single better solution which corresponds to the structure, but we have a Pareto front in both the searches. And once we have observed the structures that are on the Pareto front, we see that the structural motifs observed in our solutions are also observed in the best guess nanocluster. And also we have a better fit than the previous best guess cluster. So all these structures are better PDF fits, and also they are like bulk structures. So we can actually perform theoretical analysis using the structures that we got from the FANTASTX search. So in summary here, we talked about two different software, the Ingrained-STM mode, where we can get the surface structures from the STM image, and also the Ingrained-TEM mode, where we can get the 3D grain boundary structures from the TEM image. And we showed how we can use these atomistic structures to leverage the capabilities of theoretical calculations in understanding the properties and behavior of these materials in applications. And also we showed about the FANTASTX software, where we combine the theoretical calculations along with the experimental mismatch so that we get higher like metastable or stable structures that are experimentally observed, like intermediate structures in reaction phases or interfacial structures in grain boundaries and so on. So with that, the presentation part is done. I'm happy to take any questions. And if you like to access the softwares, please reach out to me at this email. So right now, both the software packages are not public. So I need to give you access individually if you are interested. Thank you. I'll stop sharing the screen and Joshua can continue with the STM mode walkthrough.
All right, so just checking one more time if there are any questions about what we discussed.
Yeah, questions could be typed into the chat, or just unmute yourself.
Yeah, I have a question, Joshua. So when you were presenting, you mentioned about the bias voltage coming from the experiment, but in the simulation, you don't have a measure for that, or you are not giving it as an input. Is that right? So you have a single simulation output, that could correspond to either voltages? Or is there a way you can also have the effect of the bias voltage in your simulation?
So what ends up happening in VASP, the DFT software that we're typically using for these calculations, is you set a window. So you say, I want you to produce the partial density of states relative to the Fermi level from this floor to this ceiling. And what we normally do is we set the experimental bias voltage in the middle there, and then plus or minus some window on that. This is because, again, DFT is an approximation. So whereas the experimental bias voltage is measuring relative to the Fermi level of, say, 1.3 volts, that might correspond to 1.2 in the theory or 1.4 in the theory. And so we produce data for a window around that point from the experimental calculation, and that's one of the things that Ingrained optimizes. It scans through that window to figure out, okay, well, maybe it is 1.3 and it's a good match to the experiment, or maybe it's 1.35 or so forth on.
Okay, thank you.
All right. If there are no other questions, then I will begin sharing the demonstration portion to go over how this will go. I'll be sharing the Ingrained-STM, reminder, Ingrained Scanning Tunneling Microscopy. Afterwards, Chaitanya will demonstrate the Ingrained-TEM/STEM. The difference is TEM stands for tunneling electron microscopy. STEM stands for scanning tunneling electron microscopy. The latter produces more data, but they both produce the images that were shown in Chaitanya's presentation. So we list both. And then he will finally go over the FANTASTX, or an implementation of the FANTASTX tool. So to start, you need to load various modules. NumPy is fairly standard, but we have various Ingrained tools that need to be utilized as well. The first step to any Ingrained optimization is having an experimental image. If you don't have an experimental image, oh, sorry, Chaitanya, did I say something other than transmission electron microscopy?
Yeah, you mentioned tunneling.
I'm sorry, that's a bad habit of mine. It is, TEM stands for transmission electron microscopy, very specifically. Thank you, Chaitanya. So anyhow, for any Ingrained run, you need to start with an experimental image. So here we have the cuprous oxide 111 facet loaded. The experimental image can be a text file, an SXM file, PNG, TIFF, etc. The important part is just that it's monochrome. Next, you have to set what the pixels or angstrom to pixel ratio is for this picture. In some file formats, it is automatically included, but if not, you'll need to take the length of your experimental image in terms of angstroms. So if it's nanometers, then that value times 10. And divide by the number of pixels in that axis, and then you will get your experimental pixel size. Now, this is an image that has a decent amount of inconsistency. You can see that there are defects in the surface that disturb the periodicity of the image, and so we want to crop to the highest resolution available. And so I focus here on this range of pixels in the image to produce what you see below. So that takes care of the treatment of the experimental data. Next, it's good practice to treat the theoretical data somewhat. In the Ingrained optimization, various parameters are sorted through. But in density functional theory, specifically VASP and what I use, it assumes what is called the periodic boundary condition. So you have your unit cell, a box of atoms that infinitely repeats in all directions. When you have a surface, you simulate the periodicity by having it infinite in 2 directions and adding a bunch of empty space in the 3rd direction, such that your surface of the material ends up interacting with vacuum, and then when it hits the periodic boundary, it loops back around to the bottom. By having enough vacuum spacing, you end up not having the material interact with itself, and you simulate a surface. Well, one of the issues that can happen is if your surface is close to that periodic boundary condition, that can throw a wrench in optimizing through the parameters, because you go from position 20, 21, 22 to 0, 1, 2, 3. And so you use the shift sites function in order to move the theoretical data from wherever it is in the cell to the center. So that's just done as you can see here. Very simple. Next, you need to set the angle that your theoretical image is to your experimental image. You can use this using the compare angles function, which is just a quick way to compare the angles and then rank them and select based on the initial match. You can also sort through and perform ingrained optimizations for multiple angles. But again, I recommend you speak with your experimental collaborators and discuss what the orientation is of the substrate in your experimental image, and then line up your surface such that it has the same orientation for the theoretical image as your experimental image. That'll save computation time, that'll increase accuracy, it'll improve the synergy between experimental and theoretical efforts. So moving past that, after this, you'll need to consider what machine you run, what resources you have, those sorts of things. The big one is whether you want to run your calculations in parallel because you only have access to a few cores, or in series because you only have access to a few cores, or in parallel because you have access to many cores. In either case, you'll want to, as I said, run the calculation many times, because depending on your starting point, you'll end up reaching different energy or different minima in the landscape, as demonstrated here. So we have some good fits, some correct periodicity, but you see that the white ends up resulting in a poor match. Again, some good images, and in this case, we have too much blurring going on. And so in in about half of these simulations, we end up converging on similar solutions. And so if we look at the lowest score, then we can optimize further from there. So what I would normally do is take the final settings for this simulation and then optimize further from there once or twice more, just to ensure that a ground state is reached. I have the code here on how to do that. But for demonstration purposes, I'll just take the cake out of the oven and show here what ends up being the image that I showed in the presentation of the experimental image on the left, the STM simulation in the center, and an overlap of those on the right. And then we have the predicted crystal structure. And from here, we can calculate binding energies, as this is a catalytic material, so we can calculate binding energies of molecules on the surface. We can calculate the stability of this phase versus other competing phases. We can strain and stretch the system to see if that affects catalytic properties. We can do all sorts of theoretical efforts now that we have a better guarantee of what the actual underlying crystal structure is. So now Chaitanya will present for the transmission electron microscopy tool and the FANTASTX tool.
Yeah, thank you, Joshua. So first I'll go through the Ingrained-TEM mode. So similar to the STM mode, first we will import the modules necessary from the Ingrained package. So these are like slightly different from the STM mode. And so the one of the first things that we need is the experimental image. So Ingrained supports different formats. You can provide a PNG image or a TIFF image or also the raw DM3 format image. So here we got the DM3 format from our experimental, from this particular work, from this author. And typically we prefer the DM3 format because it does not involve any post-processing. And it also has the metadata, which includes the pixel information corresponding to the size. So here we have such a DM3 image corresponding to the cadmium telluride and cadmium telluride grain boundary. So this is the experimental image that we got. In the previous example, sometimes there will be defects or like blurry regions in the experimental image. So we want to crop into a clean region. So here, just for demonstration, we are doing some cropping on the this edge. So basically, we end up having similar image here as the target. And then once we have the experimental image ready, so all the input parameters from for the TEM mode goes into the config.json file. So in this file, we provide the information about the top grain, which is lab 1 here, like the chemical formula and the space group. Ingrained will use these information to pull the structure from materials project database. And then we also provide the UVW project and upward, which is the direction corresponding to the perpendicular to the screen and also in the upward direction. And the tilt angle is sometimes we have the grain slightly tilted by 1 degree or like 5 degrees or 10 degrees, which is still same UVW upward and project, but slightly tilted. If it's too much, then we have to change the UVW upward. So again, this is like somewhat trial and error, but it will be in the range of we can find it easily. So with these information, next we provide the constraints for the Ingrained optimization. Here, Ingrained will create a supercell, which is like large enough, and we give the range within which we want the slab, the supercell to be. So the larger the atom or the width or the depth we give, Ingrained will have the opportunity to minimize strains by that degree. But at the same time, if we want to perform DFT calculations or other like theoretical simulations with the structure, we want to be careful with the size so that if you go beyond like 30 or so angstroms, the number of atoms will be in like above like hundreds, like 500 or 1000 atoms, which is impossible to do DFT calculations with. And we also need the pixel size. Again, this can be optimized. A rough value is enough, but the metadata in the DM3 file will be used in this particular case. So once we have the config.json file, we'll create the bicrystal here. So here, it's pulling the respective grains from the materials project database, and it will return the bicrystal structure in a POSCAR format, and also the strain info in the POSCAR in XN along the width and depth. So this information will also be written in the file. And what we'll get is the bicrystal POSCAR, which is just again the structure, and we can use that. So this is the bicrystal POSCAR. So once we have the POSCAR, now we simulate the TEM with the POSCAR, and Ingrained uses Ingrained-STM package, which is like a convolution HIDF images using independent atom model for the TEM images. So basically it uses the atomic number of the atoms to create the simulated TEM image. And there are various variable parameters that can change the quality of the simulation, like the defocus here, or the pixel size. And we can also incorporate the shear along X direction and Y direction, and stretching or compression along X direction, Y direction. In the current example, we don't need to do that because the image looks fairly clean. But if we want, we can also incorporate these as variable parameters. So once we define that, if we run this, the ingrained optimization will run. I'm not going to do this now. It will take anywhere between 30 minutes to 1 hour, depending on the problem. So I already have it here. So if we just run it, so right now you're viewing the carbon cluster at CNM. This is a cluster which has several CPUs and GPUs. So I'm not actually going to run this. I'm just going to demonstrate how it looks if it runs properly. It may take a minute or two. But before that, we can also see the completed run here. So you will have the progress.txt file, which includes each iterative step and the parameter values for each iterative step. And each of those steps can be visualized. So this is step 1, step 2, and each step, this is the experimental TEM, this is the simulation, and this is the fusing it found for this particular simulation. And in the initial structure itself looks like a fairly good match. And if we see the final output, we see that the defocus value has changed, and we have a better alignment with the experimental near the boundaries, and overall better FOM, figure of merit score. So if we go back here, you can see that it is running. I'm going to stop this because I'm on login node. And yeah, so each step will have a specific set of variables, and you can get a figure of merit. So finally here in the example that I showed, the best one figure of merit is around 0.22, which is the best fit that Ingrained found. So yeah, this is the walkthrough of the Ingrained code. Please let me know if you have any questions. If not, I'll continue with the FANTASTX notebook. So again, here we are going to show an example where we are going to find the interfacial structure in the grain boundary of cadmium telluride. So the experimental TEM image, we'll start with the experimental TEM image here. Clearly, in this particular image, we have some regions with loss of information and noise. And we choose first we need to trim the experimental image so that we are making it clean and free from any defects. So in this particular example, we chose this particular area in the middle to be our experimental target. So once we have this, so the second step is to use Ingrained with this experimental target, similar to the previous tutorial. We want to find the best alignment of top grain and the bottom grain before we go and run FANTASTX on the interfacial region. So again, to minimize the search space for the FANTASTX and to maximize known information from beforehand, so it is essential to do Ingrained optimization. So here we have found the grain boundary structure with best alignment in the top grain and the bottom grain region. And the interfacial atoms here are removed because that's what we will be optimized. We'll be optimizing using the FANTASTX package. So in addition to the providing the grain boundary structure, Ingrained also provides the optimum simulation parameters for the simulated STEM image. So in this case, we found the pixel size interface width is the width that we want to add between the top grain and the bottom grain near the interface. So if it is a positive value, we will have a larger gap between the both the grains. If it is a negative value, we will have overlap of both the grains near the interface. And defocus corresponds to the simulation of the grain boundary structure. So we provide these input parameters from Ingrained. I mean, the optimized parameters from Ingrained. So these are the optimized parameters. And here just we are making sure to check the comparison score before we run the FANTASTX. And in order to run the FANTASTX, we did the first part, which is we got the experimental image and the grain boundary structure, and the region is also like defined corresponding to the structure that we want to search within. Now, Ingrained has, FANTASTX has these different experimental simulations and geometries, and all these input parameters corresponding to different modes of operation of FANTASTX should be provided into one file called the input.yaml file. And I'm just going to walk through some of the input parameters for the input.yaml file, but actually a thorough documentation with all the different YAML file parameters can be found in this in this file in the GitHub repository. So for this particular tutorial, we will just see the common parameters, and the common parameters are the parameters that are irrespective of the geometry or the experimental simulation technique. These parameters should be provided to the algorithm, like the GA or Bayesian hopping related parameters, like how many total number of structures, like total population, and how many random initial samples, the initial population we want to do. And the pool corresponds to the cream of the population within which we will select the parents. So everything beyond the pool is discarded, is not considered for creating child structures. And mating constraints, which is like how many parents, like whether 2 parents or 3 parents to use to create a child structure, and whether to attach them like directly, or you want to flip and attach. So you can also choose those kind of operations. Similarly, for Bayesian hopping, we can choose the region within the cell within which we want to perturb. So if we want to perturb or do a larger jump in the potential energy landscape, we want to give a larger box within which we want to vary the atoms. Or if we want to just focus on a certain region within the structure where we are fairly confident about majority of the structure, but in a certain specific region we want to optimize the local atomic configuration, then we can use this perturb box to specify that region. And the jump fraction is the how much we want to perturb using for each atom using the Bayesian hopping. And other parameters that are common is the selection parameters. So which specifies basically whether we are doing a multi-objective search or a single objective search, and how many models do we want to consider when we are constructing the Pareto, and what operations to use and what are the frequencies to use. Like for example, here we are using a fixed operation, but if you can also mention auto-adaptive, which basically adapts these frequencies which corresponds to the operations, like the genetic operations. So it depends. So auto-adaptive makes sure that each of these genetic operators is getting enough representation in the final population. So we can do that, or we can also keep it fixed, like in this case. And we have to specify the energy code related parameters, for example, whether we are running WASP or LAMMPS, and we also have to provide the input files corresponding to the code that we are using in a separate folder. And fingerprinting is sometimes we end up choosing different structures, but they relax into a same local minima. So if a new structure that we are creating is already existing in the pool, then we want to make sure that we eliminate this new structure, because that kind of makes the pool bias towards the known structure by increasing its count in the population. So this is also very important. And the Z bounds here is specified specifically for the grain boundary geometry, because when we are comparing the fingerprints, the top grain, majority of the top grain and the majority of the bottom grain are identical for all the candidates. And we want to make sure that the fingerprinting does not eliminate candidates thinking these are same by comparing their top grain and bottom grain. So we want to select the Z bounds, which corresponds to the interfacial region in these grain boundary structures. And finally, we have the parallelization parameters that are common for different FANTASTX searches. So FANTASTX uses Dask package as a backend for its parallelization. So here we can use a PBS cluster or a Slurm cluster, or I think right now it supports PBS or Slurm, but it can be extended to other types of schedulers if there are any needed. And we specify how many number of workers we want. So the FANTASTIC's main algorithm runs on a CPU set of CPUs, which we call master, and it initiates these workers. So we can specify like how many workers we want to initiate. And all these worker specifications are given here, like what are the memory requirements, what are the number of processors needed. We can also request for GPUs if we like, and also the account information for charging. So these details specifically are present in your job script. So you can enter these corresponding to your particular local machine. And each of these workers will run one VASP calculation, one experimental simulation. And if it's done with that, it will start with another VASP calculation and another experimental simulation. And each candidate will be evaluated one after other with whichever worker is free at the time of its generation. So, so this gives a maximum efficiency of all the resources that are used within the FANTASTICS framework. So with that, we enter into the such specific parameters. Here we can, this is called structure record keyword, which includes information like whether it is a grain boundary search or a cluster or molecule or surface. That information is provided here, and the corresponding parameters that we use will vary depending on what geometry we specify here. For example, for the grain boundary, we have to specify the interface thickness and the initial grain boundary structure. And okay, yeah, sorry. And the initial grain boundary structure that we got from Ingrained, the interface thickness, and also these correspond to the selective dynamics flags. So which basically means within the VASP calculation, we want to freeze all the atoms below this Z coordinate and above this Z coordinate. With that, for example, for the nano cluster, we have to specify the size of the box and the size of the nano cluster. And here we have like a 18 angstrom by 18 angstrom by 18 angstrom box, and the maximum diameter is 7 angstrom. So it basically avoids interaction of the nano cluster with its periodic image. So we have to choose the box size appropriately according to the diameter. And similarly, we have different set of parameters for surface and molecule geometries. And the next set of parameters is the composition space. Here, we know that the interface contains only tellurium atoms, so we keep the cadmium atoms to 0. But even though it is 0, we still have to mention the cadmium species and the hydrogen species even though they are not varied in the search, because this will tell FANTASTX to run VASP calculations with these species in the structure. So if we don't give cadmium or hydrogen here, then it will run into errors when it's trying to run VASP with only tellurium, whereas the structure contains cadmium, tellurium, and hydrogen. So the composition space and the chemical potential for each species should also be provided. And this will vary the results significantly. So sometimes we have the oxygen-rich region in a oxide material. Sometimes we have the metal-rich region in an oxide material, and we can choose that. We can vary the environment by choosing appropriate chemical potential. And here we are just using the bulk as the reference phases to get these chemical potentials for each of the species. And finally, we have the experimental characterization data related parameters. So right now it supports 5 different types of experimental characterization methods. So here I show 2 different examples with grain boundary with STEM image and PDF data with the nanocrystal or bulk structure. So first we provide the ingrained optimized parameters as input from here. And also if we want to crop the simulated image before comparing with the experimental image, and also we can resize the image so that the simulated image and the experimental image are of this specific size when we are doing the comparison. So all these input parameters can be set for the grain boundary search. And for the PDF simulation, these are all parameters related to simulating a PDF from the structure using diffpy package. So for each experimental characterization data, we have different set of input parameters that are specific to that particular backend package. So for XRD, we have GSAS2 scriptable, and corresponding parameters should be provided there. So now we have the input file, the bicrystal Poscar, and the experimental image. And now we can go ahead and run the job. So I cannot run it on my local machine. So again, I'm switching back to Carbon. So here I have the input file, the Poscar, and in the inputs, I have the experimental image and the VASP files, which is basically the INCAR, K points, and the individual podcasts corresponding to each species. And if we have lamps, we need a input file for lamps for minimization, and also a potential file for lamps. So depending on lamps or VASP, these will change, and those have to be provided here. And once we have everything ready, I will just change the hours here to just 1 so that it starts quickly. Also, I'll change it in the input file. So this is the input file with all the parameters that I just showed. So here I am also changing the task workers to be just 1 hour. So just to see if it will start quickly. Yeah, it started immediately. It will take a while, like few minutes before we can see the how it is doing the parallel calculations and what are the outputs that it is generating. Before that, I have a completed run for FANTASTX as well. So here we created several calculations. So each calculation, okay, this is a refined one. I'll go ahead and show a calculation here. So this is the completed calculation. So we can see in the calcs folder all the 200 calculations that ran, and in each calculation, you would have a relax folder, which is the structure relaxation. And in some other experimental simulations, we may have to do some other optimization, so which will be done here. And in the relax, you can actually visualize the image corresponding to this particular relax structure. And also you have the WASP calculation data, and you can use this data for developing a force field or something with all the WASP data you have generated here. So this is the simulated image. Like you can see, it's no good, and the top grain and the bottom grain are fixed, and the interface is varied here. And the next thing is the data file, which includes the label for each calculation and the total energy for the model. This objective function 0 corresponds to the objective function value after we, which is calculated using the chemical potentials we provide. And the objective function 1 is the experimental mismatch. So these two are minimized, and this is what we plot in our Pareto plots. And in addition, we can also see the inheritance for each model, like if it is mating, which parents it has, if it is basin hopping, which parents it used to basin hop, and the operations can be seen here. Now if we see, as you can see, all the workers have started. So all the 10 workers have started, and if we go back to the tutorial folder, you can see the calcs folder is created, and these calculations are already started running. Yeah, so I'll just cancel this for now. So if you just cancel the master, so this is the master job, and all the task workers are initiated from the master. So if you just delete the master job, then all the workers will be eventually deleted. So with that, we can go to the analyzing the results part. So once we have the data file, and we are going to load the scripts to analyze, and we can see in total we have 210 calculations evaluated. We specified a population of 200, and we are using 10 workers. So there is an overhead of 10 calculations. So the total becomes 210. And now we are going to construct a Pareto plot with this convenience function. And if you do that, you'll see this is how the data is distributed across objective function, energy, objective function, and the mismatch. As you can see, for the same energy, we have several different mismatch values. This is probably because we have a same local minima, but the simulation is probably slightly misaligned with the experiment. So we are getting a slightly different mismatch error. And so we are going to remove these duplicate structures. So again, we are going to use the same fingerprinting parameters in the that we provided in the input. And once we identify and remove the duplicate structures, we can see that we have a total of 74 models out of 210. In this particular example, we have several duplicate structures only because the search space is very small, and we kind of overdid with the number of DFT calculations. And now with the unique calculations data, if we try to run the Pareto convenience function, we get an error. This is because I mean, we can actually find the cause of the error by just plotting the unique values, objective function 0 and 1. And we can see there is only one Pareto point, which is non-dominated on both axes. So you cannot construct a hull with just one Pareto point. So that is the error that we are seeing here. And if we just go ahead and look at the structure, you can get the ID for the lowest structure and objective function 0 and 1. And if you try to plot both the simulated and the experiment, you can see that it is a pretty good match. And this is the structure POSCAR corresponding to the final solution. Yeah, and in the presentation, I showed some of the other examples where we have like a set of solutions which are non-dominated. In those cases, we collect all the Pareto points, structures and images, and we can do like further analysis like by relaxing it with like a more lenient or more finer grid to get accurate data and do further characterization. Yeah, with that, the hands-on session is also complete. I'm happy to take any questions regarding the presentation or any of the tutorials. Yeah, thanks.